Welcome to Drone Systems and Control course, Lecture 6. Lecture 6 talks about sensors in drones. Particularly, we are going to talk about sensors which is useful for control and navigation of the vehicle. What is the Lecture 6 objective? You will be understanding different type of sensors, their functions of the sensor used in UAV. UAV here I meant a drone which is a multi-rotor system. Learn how these sensors contribute for drone navigation, control as well as autonomy of the drone, and we will also explore how we do the sensor integration, where to place these sensors such that the measurements are much more accurate. Okay. Now, when we are trying to classify the sensors, we have sensors required for navigation and position. For example, we have GPS sensor. The GPS sensor tries to provide the position of the drone and it also provides the velocity, right. We have orientation and attitude sensors, that is to determine our Euler angles, roll, pitch and yaw, and angular velocity, what we call P, Q and R. We use IMU and magnetometer. Magnetometer will give me the heading of the drone, in what direction the drone is flying. And we also use sensors which talks about the context of the context in which the drone is flying, environment in which the drone is flying, right. Moment we just bring in the drone in a practical world, right, we need to know what height it is present. I can use ultrasonic sensors, radar and LiDARs, right. I can also measure the wind speed if I want to handle it accurately. We can have those sensors also, right. There comes visual sensors, perception sensors I will call it, visual perception sensors. Basically they just talk about the environment like camera. You can have a thermal camera, you have a spectral camera, you can have a depth camera, you can have a LiDARs, right, or you can have a 3D radars, will give you how the context is being present for the drone to navigate, right. It will also help the drone to localize where is it in that particular context, or it will also help you to do the terrain mapping and so forth, right. There are sensors which required for feedback or control purposes, right. We will look into that also in this particular course. For example, I will use sometime optical flow sensors, I will also use barometer specifically for control purposes, right. I will also use closed loop actuators. I want to know whether the actuators is providing the control output what I am demanding for. Let us first look at the navigation sensor, right, that is a position sensor. I am looking at global navigation system, right. So, I am using a satellite based navigation system to get my position at any given time t, right. So, I can use GPS or GLONASS, or I can know Galileo, or even we can go for our Indian satellite system to get the position of the drone in a global frame of reference. What we are trying to measure? We are trying to measure the position, that is latitude, longitude and altitude at which this particular drone is present, right. What is the speed at which the drone is moving, the ground speed, and time synchronization. So, we measure the time delay between the satellite transmission and receiver. We just use that information to estimate the location of the drone and speed. Where it will be useful? It is useful for waypoint navigation. So, you want to move the drone from one latitude longitude to another latitude longitude, you can use it, or you can use it for geofencing. So, you say that my drone have to fly within a boundary, right, it should not cross the boundary, then you can use a fencing system so that the drone will operate within the boundary. We will discuss about that later part of the lecture, and we wanted to use it for autonomously landing at a specific latitude longitude, or you wanted to survey a specific area, or you wanted to use a mapping. In those cases GPS plays a very important role, right. What is the limitation? If you are flying the drone in a cluttered environment, right, you may not have accurate positioning system. We all experience, right, when we are driving a vehicle in a cloudy day or between densely populated buildings when you are there. So your positional error in goes haywire, right? So that's become a bigger problem. Second, if you are operating a drone indoor, GPS based navigation will not work well. You will have a poor signal which will affect your positioning accuracy, right? Sometimes some reasons there may be jamming or spoofing that will also affect the positional accuracy of the drone. Okay. Usually these antennas are, the GPS antennas are placed on the top of the drone so that you don't have obstructions, there is no multipath, so that you can get a perfect positioning accuracies, right. Now very important measurement is an inertial measurement unit, IMU, right. IMU is a combination of the sensors used to measure inertial parameter of the vehicle which is mounted on the vehicle, right. So I am trying to get, what are this parameter that I am trying to get? I am trying to get the angular velocity, I am trying to get the acceleration of the vehicle, I am also trying to get the pose of the vehicle, right. So you have, typically there are three subcomponents present in IMU. One is the gyroscope. What is the function? It measures the angular velocity in all three axes, right. So I get it in radians per second. Then you have accelerometer. It measures the linear acceleration along all the three axes. I measure either meter per second square or in G. And then you have a magnetometer. It measures the earth magnetic field strength and the direction in all three axes so that I can try to get the pose of the vehicle, right. So usually all these measurement X gyro, Y gyro, Z gyro, X acceleration, Y acceleration, Z acceleration and XYZ magnetic field measurements, I fuse them together to get my Euler angles, that is roll, pitch and yaw, position of the vehicle X, Y and Z, velocity of the vehicle Vx, Vy, Vz and angular rates also PQR. Now let us look at the classical inertial measurement unit. If you are looking at a mechanical gyroscope, it is a typical mechanical gyroscope, right. You have a gyroscope frame, you have a gimbal, right, and the axis about which the rotor is going to spin, that is a spin axis. I can measure, if I have the mechanical gyroscope kept on the vehicle, I can measure what is the rate of angular motion in that particular axis, right. If I am looking at a mechanical accelerometer, it is a spring mass damper system, right. So how this mass vibrate with respect to the acceleration of the vehicle, I can measure that and I can use it, right. There are different types of inertial measurement units are available. One is a mechanical measurements, another one is optical measurements and third one is micro electromechanical system, MEMS what we call, right. So mechanical measurements is going to be heavy, optical ones are very precise but it is very costly. So MEMS based systems are playing an important role in robotic navigation as well as drone navigation. The reason is there is a low cost, lightweight and power efficiency, right. So that is why we try to use this MEMS based IMU unit in drones, right. How does the MEMS based accelerometer, how does the MEMS based gyroscope function, we will discuss them in details in subsequent slides. Okay. I will explain when we go there. Let us look at components of it. What are that we are talking of? We are talking of accelerometer, gyroscope and magnetometer, right. 3 accelerometers are going to be there in 3 axes, 3 gyros are going to be there. So it has become 6 axis IMU system, or sometime it will be 9 axis if you have 3 more magnetometer measurements are there, right. What do? We estimate orientation and motion of the UAV, right, and these are required in high frequency so that I can provide the control, right. What is the advantage? They have very fast response, independent of the external signals, but magnetometer do get affected by interference, right. So we need to take into account. There are limitations in estimating the orientation of and motion of the UAV, right. The error accumulates over a period of time, that will cause the drift in the drone, it may not be in the same position, right. So you may have to fuse this IMU system with external measurements, right. For example, I can fuse this with the global positioning system so that my positioning error can be minimized, right. Why this error happens we will discuss when we go in individual MEMS based accelerometer and MEMS based gyro. We will discuss this in detail, right. So, another aspect I just forgot to mention, and these need to be kept at CG point so that the vibrations does not affect, okay. And usually we will add an additional isolator to minimize the vibration gets transformed, and unnecessarily the control input trying to correct the small vibrations which happens due to the wind. So, let us look at MEMS based accelerometer, right. So, you have a mass, you have a fixed plate, you have a movable plate, you have a spring and which are attached to capacitance measurements. Any acceleration happen in this axis will just change the movable plate. If the movable plates change its position, it will change the capacity. That is where we will be able to measure the acceleration very precisely here, right. It detects a linear motion, that is a forward backward or left right and up down, and we can just get the gravitational acceleration, the static components, and it also helps in estimate the drone orientation in combining with the gyro. It also helps you to estimate the change in thrust, or if you are trying to look at the free fall or collision detection, all this will be very useful to use MEMS based accelerometers, right. How does it work? It is a tiny mass inside that gets an acceleration, and that led to change in capacitance or change in resistance that used to convert the acceleration values, and that will convert the electrical signal, and we can do the conversion into acceleration accordingly, right. Now, what is the advantage? They are compact, lightweight, low power, very fast response, no need of external references for this. It measures both motion and gravity. Drift noise can be affect the accuracy over a period of time. What I meant drift here is we are measuring acceleration, but what is our interest? Our interest is to measure the position of the drone, x, y, z position of the drone, right. So, what we are doing intuitively, if I wanted to explain that what does the drift means, we are trying to do the double integration of the acceleration, right, to get the position information. If the initial position is error over a period of time, and due to bias which is present in the sensor also, over a period of time the positional error will keep increasing, that increasing proportional to time square, right, t square. So, which required some kind of a fusion to minimize the drift, right. So, usually combined with gyroscope and magnetometer to reduce this error, but if you have a global positioning system, another sensor which will help us to reduce this drift much further. We will discuss this little later, okay. Now, let us look at a MEMS based gyroscope. It is a sensor that used to measure angular velocity, a rate of rotation. So, imagine I am just going to put gyroscope in x, y, z axis. So, I can find out what is the rotation angular velocity in x and y and z directions accurately, right. How does it work? It detects rotational movement of the drone. I showed you a mechanical gyroscope earlier, and the same way it is just going to look at it. I can get attitude of the drone, that is Euler angles phi theta psi, okay, and this attitude will be useful for flight stabilization of this drone, and angular rate is useful for how fast I wanted to turn in a specific directions when we are talking about obstacle avoidance, right. And I also need to do the pose orientation of the vehicle, in what direction the drone needs. Suppose if you are doing inspection of a building, right, and you want camera is mounted in the front looking forward direction in x axis. Your drone need to position in such a way that the x axis is perpendicular to the wall which you are trying to inspect, right. So, you need to have the perfect orientation alignment. So, that control will also be used. For that you need these gyro measurements. How does it work? It uses a Coriolis effect or vibrating mass which shifts under angular motions. right. The shift is converted into electrical signal and that is proportional to your angular velocity. What are the advantage of using MEMS based gyroscope? They provide real time high frequency measurements. They are independent of external references. Here we are not using any GPS or anything, and they are very fast response and hence they will be useful for closing the loop to create stability of the drone, right. What are the limitations? Similar to MEMS based accelerometer, they also drift over a time, right. Any small changes in zero rate level, that what we call slow change in zero rate level, accumulation of error over a period of time, it happens due to the integration of the rates, right, to get the orientation. They are very sensitive to the vibration and temperature. You have to maintain the temperature and you have to isolate the external vibrations so that your measurement on your post becomes Euler angles becomes more accurate, right. How do we use? We combine IMU as well as gyroscope along with the magnetometer to get our measurement unit, right, inertial measurement unit, or we also call it attitude heading reference system, AHRS, right. This has a sensor fusion algorithm. Sometimes we use extended Kalman filter. In lecture 8 we will discuss about filtering or parameter state estimation, where you will understand how we fuse these informations to get the states of the system, and that will improve the orientation accuracy significantly, right. Now let us look at the magnetometer, a sensor that used to measure the intensity and direction of the earth magnetic field. Using that information I can find out the heading of the drone, right. I can just look at the heading, whether with respect to magnetic north, where is your heading, right. It is a complementary sensors in IMU and AHRS. It is critical for accurate yaw estimation, particularly when you are talking about when global positioning system is not available, right. It works on the principles of Hall effect, magnetoresistivity technology. I measure the magnetic field along all three directions to get out my direction of orientation or heading of the drone. It is useful for navigation. It is useful for sensor fusions to get the orientation accurately to minimize the drift. It is also useful sometime when you have a GPS is not there, you want to get the drone back to home, or you want to have autonomy in the drone, you need heading information, right. Advantage, they provide absolute heading reference, lightweight, low power, but limitation, they are prone to magnetic interferences. When you are having a small onboard computer, right, and you are connecting the computer to the external sensors like camera and LiDAR, they do have magnetic field produced at the point. For example, USB 2 or something you are using, it could create magnetic field. So where this particular sensor is located play an important role. We have to minimize as much as possible the interference with respect to magnetic field. If there is a power line going, if the drone is flying closer to the power line, it gets influenced by the magnetic field around it, right. Best practice, or if you ask me, the placement, mount away from high current components, right. Use external magnetometer or extended bones whenever you need, when you want a precision you are looking for, right. You use an onboard campus calibration regularly to just avoid any errors in heading, right. You have to do the regular calibrations whenever you are using the drone for autonomous navigation in a particular mission, right. In addition to positioning system, IMU, we also need to know height, right. We can use altimeters, right. Altimeters measures the atmospheric pressure to estimate your altitude, right. What is the working principle here? Based on the inverse relationship between altitude and air pressure, I can just look at the differential air pressure to find out the altitude, okay. It will help us to know how fast the drone is descending by just looking at the pressure variations, right. I can position at a drone at a specific altitude. We can just use for altitude hold or even precise landing rate at which you wanted to descend, right, or rate at which you wanted to ascend. We use altimeter, right. Here you can use MEMS based altimeter. The Bosch, I am just giving an example, BMP 388, or you can look at MS 5611. These are MEMS based. What is it useful? It is useful for your takeoff and landing. You wanted to take off from a ground, go to a specific altitude and hover, or landing precisely at particular point. I mean, for point you need XY measurements, but you wanted to descend rate at which you wanted to descend to come to an ground, you need this altimeter. Okay. You can also use why we use a barometer. It is high resolution, lightweight, power efficient. It works both indoor and outdoor. The problem is the weather and temperature variations affects this. It is very sensitive to the weather and temperature variations. The turbulence will also, and sometimes the rotor downwash will also affect the measurements significantly, right. Best practice or where to place, you shield the propeller flow and vibration so that the measurements of altimeter is accurate. You mount close to the drone CG point and use a foam covers to stabilize pressure readings properly, right. If you want to use ultrasonic sensors, also possible to measure. It basically sends a sound waves to measure the distance to the object, right. Time of flight sensors are there. Basically a sensor emits a burst of ultrasonic sound waves and they receive. The time it takes to go and get reflector from the surface is to measure. That is what we call echo. Using the echo I can find out the depth, right. How do you calculate the depth? Depth or the distance is velocity of the sound in time of flight times time of flight divided by 2. The echo gets reflected, travels back the same distance, right. So that is why we are just dividing TOF by 2, that will give you the distance, right. So we use sometimes ultrasonic sensors for altitude hold, particularly they are very effective for indoor navigations where you have a flat surfaces, you can get it done, right, or you can also use for obstacle distance detections. The problem is the characteristics of ultrasonic sensors get the conversion of the distance to velocity measurements. We need to take that into account, and it is not for long range, right. So we need to use it for short range obstacle detection, and it can only tell you the point measurements. It does not tell you how big is the obstacle, right. So generating path for that will become little tricky. Or you can use a LiDAR based altimeter, single point LiDAR. Sometimes we do use a single point LiDAR. I am just showing an example here where it is mounted exactly at the CG point, right. It is also low cost, it is energy efficient, easy to integrate. You can just combine with the microcontroller, you can just get the position altitude information and send it directly to your flight controller. It has limited range again. It has a low resolutions at long distances. Performance get affected if the surface roughness varies, right, or there is a background ambient lights comes into picture, the performance of the LiDAR gets affected significantly, right. Usually you mount downwards to get a reliable altitude control, position the sensors to get the better coverage. You have to just keep it in such a way that it does not get obstructed due to the motion of the drone. Okay. In a summary, we talked about very important sensors which requires to stabilize the aircraft. These are what we call necessary sensors. If you wanted to get automatic takeoff, landing, automatic moving from waypoint navigation from point A to point B, right, you need these sensors. Global positioning systems, GPS will give you the latitude, longitude and altitude. It also gives the velocity measurements. Then you have a IMU, inertial measurement unit, which is required for your attitude stabilization and inner loop control, right. You are measuring the orientation and position information. Then you have additional sensors to get your magnetometer to get the heading, altimeters to get the altitude, right. You can use either barometer or you can use LiDAR or even use ultrasound to get your height. Depends on applications, you need to select which sensor is needed, right. So, we talked how these informations are fused to get your position and attitude that will be used for control. That is why I said these are necessary sensors for drone stabilization and navigation. Thank you.